Hi guys, I wanted to give you a little bit of help instruction this week on Chapter 10. I'm going to go over a few of the topics that you'll come across in Chapter 10, in addition to you looking over the helps on the My Lab and Mastering. This will help you complete those problems. First off, don't forget good old trusty Pythagorean's theorem. Okay, if you have a right triangle, remember that one of the legs, we can call it A or B, whatever, and the other one, if we square A and we add it to this distance squared, okay, it'll equal the hypotenuse of the long distance squared. Okay, and the cool thing about that is if you know two of the three sides, you can then plug them in and solve for the unknown. Alright, I'm not going to spend much more time on that. That's hopefully something you've seen before. Alright, the next topic that you'll come across that may be new to you or some of you is angle measurement, but using the units minutes and seconds. Well, you say minutes and seconds are something to do with the clock and time. All right. Also, it has to do with angles. For instance, if you had an angle, let's say that looks something like a little bit more than 90 degrees. Okay, not quite 90 degrees. We could call that 90.1 degrees. All right, using a decimal. All right, but there's other ways to express that same angle measurement, and there's more precise ways. Okay, because when you get into surveying or other aspects of the building trades, okay, they go into something called minutes and seconds. It's another way. You can think of it kind of like the tape measure. All right, we could do tape measures. We could say this. We measure something and say it's 2.4 inches. Okay, but we don't say that. We say 2, and then we say like 3/16 or 7/8 or whatever it is. Okay, minutes and seconds are the same kind of thing. We're breaking up the whole degree and we're breaking it up into parts. And so a minute, okay, 1 minute is 1/60th of a degree. All right, so if I have, let's just say I have 90 degrees here. All right, if I want to get a little more precise with that, I might say something like, and I measure, let's say I get 3 minutes. And we use a tick mark. It's not inches in this case. We're talking about degrees. It's called minutes. And then seconds takes those minutes and breaks the minutes up into 60 parts. So we get really, really a teeny amount of degree, just barely moving that angle. And let's say 20 seconds. We use 2 tick marks when we're talking about seconds. All right. So this is a precise way to measure an angle: 90 degrees, 3 minutes, and 20 seconds. Okay. Now the challenge is what you'll be required to do is to convert from an angle written with degrees, minutes, and seconds to an angle written with degrees and decimal parts of a degree. All right. And the way to do that is to recognize, hey, this is the same thing, okay, as 3/60ths of a degree, and this is the same thing as 20 3/600ths, because it's 60 times 60, because we're breaking this up into even tinier spots. 20 3/600ths of a degree. So if we were to, in our calculator, take 3 divided by 60 and 20 divided by 3600 and then add all these up, we'd end up with the decimal conversion from degrees to seconds. If we do that, we get, all right, if we do that, we get 0.05 and 0.0055 repeating. If we add those up together, we get 90.05 essentially repeating. Now, on my lab and mastering, they will ask you to round to a certain decimal point. So if they ask you to round to the nearest hundredths, then we would actually round this to 90.6 degrees. Okay, so we could either write this 90.6 degrees, or more precisely, we could write it as 90 degrees, 3 minutes, and 20 seconds. Now you can go backwards. You can go the other way too if you need to, from degrees to seconds. All right. So back to original example here, let's just see what 0.1 is in terms of minutes and seconds. All right, how do we do that? Well, just like if we were to convert from a decimal part of an inch and change it to 1/16 of an inch, we do the same thing here. We're going to take 0.1, okay, and we're going to figure out how many minutes that is. All right, we have to divide it by how many minutes are in a degree, and there's 60. Okay, so 0.1 times 60, and that just essentially moves the decimal place. We've got 6 minutes. So to convert this, we get 90 degrees, 6 minutes, and 0 seconds, because it's exactly 6. All right, if there was more, if we had to keep going to seconds, if for example on this problem here, let's say we had something like 90.41 degrees. Okay, again, we're going to take the 0.41 and we're going to multiply it by 60. I'm going to erase some stuff here so we can clear up our mind here. All right, we get 24.6. So we have 90 degrees plus 24.6 minutes. But I don't want that 0.6 minutes. I can't have a decimal part of a minute. I want to change that into seconds. Well, I'm going to take this then, and how many seconds are in a minute? Well, it's 60. Okay, so then I'm going to multiply 0.6 times 60 to change that into seconds. So in that, I end up getting 36 there. Okay, so 90 degrees, 24 minutes, and 36 seconds. All right, so those are two topics you'll come across. You'll also come across several special right triangles that you have to deal with. Okay, one of them is a 3-4-5 triangle, and we've talked about this before, but essentially a 3-4-5 triangle is referencing the sides. So if you have a triangle that has a side of a 3, 4, and 5, okay, it has to be 90 degrees. That's kind of the relationship. Or any multiple, okay, or any scaled version of that triangle. So a 6, 8, 10 would also have a 90 degrees between the two smaller legs. You can use that relationship to solve for unknowns. Okay, for instance, if you have a triangle that looks like this, then you know, okay, you know that, and it says this is 90 degrees, then you know that this has to be 4. All right, so they might have some questions like that where you don't actually have to do Pythagorean's theorem. It's just a special right triangle. All right. There's also special right triangles that they're special because of the degrees that they have. Okay. One of these is a 45 degree triangle. Okay, it has to be 90 if you think about it. 45 plus 45 is 90. All the angles in a triangle have to equal 180. So then this has to be 92. All right, and there's things that's special with this as far as the sides is they have a special ratio of the sides. Okay, the ratios have a special, and that special ratio is if this side is 1, the other side's 1, because they're the same angle, they're an isosceles triangle, and then this has to be square root of 2. All right. Now that's useful because if you're given a triangle that is a 45 degree triangle, and you're given one of the side lengths here, let's say like 3, then you know that this one has to be 3 too, because it's the same thing. So you don't have to do much math. You just have memorized this relationship of sides. All right. Now, what about finding this distance here? It's a little bit more complicated, but not much more complicated. All right. If you see that, I didn't draw it this way, okay, but if you see that the distance, this side was 1 and it went to 3, it's a same triangle, it's a similar triangle, okay? It's just a bigger version of it, right? It exploded by a factor of 3. All right, so then the answer to this over here then would be 3 times square root of 2. And my math lab might want you to put it in that way if they ask you a problem like this, or my lab in Mastering, okay? You could also approximate that with a decimal. All right. All right, the third type of special right triangle that they might give you, where you don't need to use Pythagorean's theorem to solve, okay, is a 30, 60, 90 degree triangle. Okay, and this looks similar to this. It could be this could be rotated and standing up tall and skinny rather than long and skinny, but it's the same thing. Okay, if you have those if you have a right triangle with those angles, okay, you know that the sides are going to be in a special relationship, just like this one. Okay, and that special relationship is you've got 1 square root 3 and 2, and you just have to memorize this. This is just something you memorize. Okay, if you think through it, you could figure it out. Okay, if you're familiar with the unit circle, or if you're even just thinking about Pythagorean's theorem, you could figure this out. Okay, but it's easier just to memorize these. Okay, or have them written down somewhere you can look at quick. All right, so similar to this aspect here, if you had then a triangle that was, let's say, a little bit smaller version, but you were told, okay, this is a 30, 60, 90 degree triangle, and you said that this is the distance of 1, the hypotenuse is the distance of 1, because of the same angles, you know, they're similar triangles, so they're just scaled versions of one another. Well, what did we do then from this side to this side? Okay, we multiplied it by 1/2, or we divided by 2. It got smaller, right, by a factor of 1/2. All right, so we do the same thing to all the other sides. So instead of this being 1, it's going to be 1/2, and this is going to be square root 3 over 2. I didn't have to do any Pythagorean theorem, and I could solve for those unknowns because I remembered those special right triangles. All right, one of the main last things that you're going to have to do is SOHCAHTOA. If you recall, or if you've never learned about this, this is fun stuff. What are you saying? SOHCAHTOA, is that Latin? No, it's just an acronym to help you work with right triangles, okay, that can't be worked with Pythagorean's theorem or with one of those special right triangles we talked about, okay? So if you're stuck, you know, you don't have angles that match up, it's not a 3, 4, 5 triangle, you don't have 2 of the 3 sides, okay, then another tool to help you solve for unknowns with right triangles is SOHCAHTOA. All right, SOHCAHTOA stands for sine opposite hypotenuse, that's the SO, okay, S-O-H. Ka stands for cosine, should be either, adjacent and hypotenuse. And then TOA stands for tangent, opposite, and adjacent. Okay, what the heck do all these words mean? Alright, well, the best way is just to show you with a right triangle. Okay, so if I have a right triangle here, alright, so you've got a right triangle here, and if you pick the non-90 degree angle, okay, either this side or this side, doesn't matter which one, okay, that's when you start using SOHCAHTOA. Okay, so you're going to have this information given to you, and you're going to have one of the angles, okay, and then one of the sides, and then you're required to solve for the rest of them using these relationships. And this is all that SOHCAHTOA is. It's just relationships, just like the 3, 4, 5 triangle, just like the 30, 60, 90 had a special relationship of sides. Okay, all right triangles have special relationships of sides, and they're defined by SOHCAHTOA, or this relationship. Okay, so let's just pick this angle. Let's say I'm gonna be at angle A here. Okay, so let's say I'm given angle A is it looks about like 50 degrees maybe. Okay, 50 degrees. I'm given that. All right. From angle A, then I define my relationships here. Okay, if you notice, opposite. Okay, that's kind of a direction. All right, what it means is opposite of the angle that you're looking from. So if I'm looking from angle A, what side is opposite? All right, well, it's this one. Okay, it's not even touching this angle. All right, so this would be my opposite then if I'm looking from angle A. And if I'm looking from angle A, then what my hypotenuse is, well, the hypotenuse is always the long side, so that's easy. This is hypotenuse. If this is the opposite, then this has to be the adjacent, right? Because it's touching the angle. Now, flip that around. If I were to look at the same triangle, okay, but let's say that this is, we're looking from this angle, which would be 40 degrees, and we'll call it B. Okay. Then things get flipped around, all right? Opposite of B is this guy here. Adjacent of B is this side. The hypotenuse stays the same. So it's the same. Okay. All right. Now I could define my trigonometric ratios using these relationships. Okay. So the sine of A. So if I'm looking at the sine of A, and we drop the e when we're doing that. Okay, it would equal, well, it equals opposite over hypotenuse, and it's over hypotenuse. It's always over. Okay. Sine of A equals the opposite over the hypotenuse. Okay, and you can define all of these. You can say the cosine of A equals the adjacent over hypotenuse, and the tangent is going to equal the opposite over adjacent.